So we just want to bring an end to the classification of polymers. So we have thermosetting plastics. So the first one you have is, again, both of them are made using condensation. You have urea formaldehyde and phenol formaldehyde. Again, urea formaldehyde, again, brilliant chemical resistance, great heat, again, great against heat. Can be used to, so this is the urea formaldehyde is used for glue. Okay, so again, remember I was saying it, again, if it takes a while to set, it's the cross linking taking place. It's the cross linking that's holding it up and setting. Okay, so it's using electrical fixings and casings. And then phenol formaldehyde, again, is known as Bakelite. Don't worry about that. It's a hard and heat resistant material and used in snooker balls. Okay, so you just need to take down those two things on those. Just talk about each of them again. Once you know one of them, you're all right. The next one I want to go through is just composites. So composite is a material that consists of two different materials to make a superior material. Okay, so again, you have carbon fiber. You can see carbon fiber there. See the way it's sort of, it's like a sheet. See the way it's like a sheet, it's like nearly like a cloth. What happens there is the carbon is formed into a thread and then it's woven into a sheet like that. The sheet gets placed over the mold like that, and then resin is painted on, and that is your carbon fiber. Okay, very, very strong material. Again, don't forget, just take down those points on carbon fiber. And then on carbon fiber, glass fiber, is the exact same principle, only it's glass that's used to make this sheet much cheaper. It's not as hard to make as carbon fiber. The problem with this carbon fiber sheet is very, very hard made. That's why it's so expensive. So it's low cost, turns clear when it's curing, and has excellent strength, and it's used on things like boats. So you have your different crystalline structures. So again, amorphous is a mess. So again, amorphous. So you for amorphous, your chain link molecules are they're all over the shop, like they're like that. And the reason, again, you have uniform strength because they're all intertwined. They're all woven in together. Okay. Again, it says less strength, but it's a uniform strength. Okay, it's uniform the whole way across. Okay, again, it has lower density because it doesn't need to, like, again, you can see how close these are together compared to this. Okay, so these are much closer together. They don't need to be as close for amorphous. Lower density, and the soften easier with heat. Okay, crystalline, on the other hand, is everything's uniform. Okay, like that. They're very strong this way. If you try to bend it across that line, very, very strong. If you try to bend it across that line or pull it, if you had something like a plastic bag with the crystalline structure, and you try to tear it along that line, you would tear it because it's weak along that point. It is a higher strength. Again, this way is very, very high strength because you have all the molecules working together to provide that strength. Whereas this way, you could have none. Again, might only be one or two intertwined into it, but again, depends how microscopic you want to go with it. Amorphous, a mess. And then glass transition temperature is the temperature that it's, again, there's no, for especially for copolymers, there's no melting point. Is the temperature that plastic has a glass or a shiny surface appears. Okay, and that is okay. It appears at different temperatures on different plastics. Okay, so that's what a glass transition temperature is. The temperature where it's in transition to a glass-like state or with a shiny sheen on the top of it. Again, you can see some dull matte plastics will develop a shiny surface. Okay, and so that's it, guys. That's just the finish of the thermoset plastics, or the classification of plastics.